Whiteboard Physics A-Level Lesson 67, Components and Their Characteristics. Obviously, we want to build circuits. We're interested in building circuits. So we need to put components in those circuits, things like lamps and cells and so on. So here's a bunch of components that you need to know the symbol of. Here's a cell. So we have the symbol that looks a bit like that. Now, a couple of things about the cell symbol. You'll notice that the bar on the left is significantly longer than the bar on the right. The bar on the right is drawn thicker. That's not actually necessary, but it tends to be done, but you don't need to. But the two bars are quite close together. I very often see students drawing things like this and thinking that that's good enough for a cell. That is not a cell. I don't even know what that is. Really make an effort to draw it neatly like I have there. So there is my cell. Then we've got a lamp, and there are different types of lamps. We can use an X like this, and that would be a signal lamp or an indicator lamp. We can also use a symbol that has this sort of curvy symbol like that, and that's a filament lamp. But that has rather fallen out of fashion now, so we don't tend to use that symbol anymore. And so I'll erase it, and if you want it, you can always include it yourself later. What else have we got? Well, in many circuits, we have some resistance where we don't know what the resistance is caused by. We might even have a component called a resistor, which is a fixed resistor. So maybe I should label this a fixed resistor. It's ohmic resistor, which means the resistance does not depend on the current that passes through it. Resistor. Notice that these symbols all have the wires that are trailing in and out of the component. They are part of the circuit symbol. And there's a bunch of other resistors as well. There is the variable resistor indicated with a diagonal arrow that passes through the both long sides of the symbol, like that. That is a variable resistor. And there's another symbol that's similar to the variable resistor, which is a potentiometer. But I'm not going to include that on this list either. That'll come up later, I'm sure. Then we have thermistors. So these are resistors where the resistance depends on the temperature. And there are different ways of drawing those. Thermistor. Then we have, what else should we have? Well, let's have a diode, because we're going to be talking about diodes today. And there are different symbols for diodes as well. So sometimes you'll see it with a line that goes straight through. Sometimes it's drawn without the line going straight through. I'm on the fence. I haven't decided whether I prefer the line going straight through or not. I think perhaps I don't, but it's fine if the line goes straight through. It's perfectly correct. Sometimes it's drawn with a circle around it. Sometimes not. I don't think it needs the circle, really. I'm not that bothered. So that is a diode. And there's a general idea now, which is anytime you have lines, or I should say arrows, two arrows coming out of a device, that means it emits light. So that's a light emitting diode, also called an LED. Diode, LED. We'll talk about what diodes are a little bit later. We also have light-dependent diodes and light-dependent resistors. So this is a light-dependent resistor. Anytime two lines going in, that means that it's dependent. Light-dependent resistor means that the resistivity, depends on the intensity of light. What else do we have? Well, something else that looks a bit like a heater, looks a bit like a resistor, but isn't, is a heater. It is a resistance in a sense that it has resistance, but we tend to draw it like that if it's particularly used for heating. So that is a heater. We can have a motor, and that is actually just a circle with an M in it. Also, sometimes you'll see other symbols for stepper motors and things like that. That's all their motor is. And on the subject of things that are just sort of circular symbols with letters in them, we've missed out our voltmeter, and our ammeter. So let's draw these. Ammeter, not amp meter. And I'm just going to move these to the left a bit. Boom, there we go. And okay, that's enough for us to be getting on with. We could have some others, I suppose. We could have the oscilloscope, which we met in the waves topic. The symbol for that tends to be a zigzaggy line, and that's very easy to confuse with the motor, but it is different. Anytime we have some sort of connection between 2 points, we can have terminals, so that would just be a terminal. And of course we've got switches, which I haven't bothered to draw. Switch, that's a toggle switch, and so on. So there's a whole bunch of symbols I haven't drawn. Circuit symbols, right? Characteristics. In order to measure the characteristics of a component, we need to build a circuit. And so what do I mean by characteristics? I mean the way that the current through the component depends on the potential difference across it. So measuring component characteristics. That's what we mean by characteristics. Do it like that. Is the way that the current through the component depends on the potential difference across it. So let's start by building a simple circuit, a very simple circuit, with a power supply and some component, which I'm going to just draw as a resistor. It doesn't really matter. And I'm going to put a variable resistor in the circuit as well, like this. And I'm actually going to include a switch for reasons that I'll explain in a second. Now that circuit, if we switched it on, current would pass through the variable resistor and through the fixed resistor. If we want to know how much current, we would have to connect an ammeter, just like that. And because we're interested in how much current passes through that point, the ammeter has to be connected in series. And if this is the component that we're investigating, we're going to connect a voltmeter in parallel with that component. So there we go. That is a circuit that will work. Now, we didn't have to use a variable resistor. We could have just done that and used a variable power supply, and that would do the same job. So that circuit works. Let's do one with a variable power supply. In fact, I'll do the power supply in a different symbol. I'll use 2 terminals, and I'll do this like that, and I'll write that. That's a variable power supply right there. And I'll do the same thing. Ammeter, some sort of component that we're interested in investigating, variable resistor. No, we don't need that anymore. We should just go like this. And then the voltmeter in parallel. Now, topologically, what I've just drawn is the same. The voltmeter is in parallel with the resistor in the same way in both of those circuits. Students often get spooked by the fact that I'm connecting it here and here instead of here and here. But if you understand what's going on with potentials, you'll see whether I connect it here or here, here or here, those two are at the same potential. So it doesn't actually matter. Once you get your head around what potentials are doing in a circuit, all of this makes a lot more sense. At least I think it does. So, right, let's appease you and let's do the voltmeter connected like this. And that's not the only way. We can also design a circuit using a potentiometer. So this is a device that has a fixed resistor, and then usually it's a slider, or you can get potentiometers that are rotary ones, so you can tap off some of the potential difference. we tap off somewhere along that potential. So it's like having a wire that you can, or part of this circuit here that you can slide up and down here. And the higher up it is, the more of the 1.5 volts potential difference there are between that and the ground. And the lower it is, the lower it is. So that is what we do with this potentiometer. We connect one side to there, and then the bit in the middle slides up and down, so we can select how much of that 1.5 volts we want. Again, having that symbol, the potential model in our head is a better way of going. So let's say we have a simple power supply. Maybe it's a battery this time. The ... indicates we don't know necessarily how many cells are in it. And we're going to use our potentiometer. So that's a fixed resistor, but then we tap off some of it like this. Notice that when we connect to the circuit, we draw these little blobs in order to indicate a connection. I want the ammeter in series, and then I want my interesting component, and then I want to connect my voltmeter as well. And that's another very good circuit using a potentiometer. Let me just write that down. So using potentiometer, using variable power supply, and using variable resistor. The one in the middle and the one on the right are the best ones. Anyway, you can use these to measure resistance of a component. You just stick the component between the two terminals of the voltmeter, so where the fixed resistor is in each of these circuits. You just connect the component in there, and then it will, let's just color that in. You just connect that, and you can read off the potential difference across it and the current through it, and then use R equals V divided by I to calculate the resistance. That's a very straightforward thing to do. But if we choose to change the potential difference across the component, we can then see what the current does as we do. And we end up with different relationships between the potential difference and the current depending on the component. So for a fixed resistor, it will look a little bit like this. We will have our graph drawn like this. We'll go negative as well as positive potential. Yeah, that's the other thing. If we're talking about energy, how do you go negative? Whereas with potential, there's no reason why we can't go below the ground as long as we come back up again. You see, there's lots with this model. It's a much better model. Anyway, I'll stop. Let's put here on the x-axis, we'll put potential difference because that is our independent variable. That's what we're choosing to change. We'll put current on the y-axis because that's going to change as a consequence of the choice of independent variable, and you end up with a straight line, just like that. That's what a fixed resistor does. Now, if you have a lower gradient for a fixed resistor, that will indicate a higher resistance. But don't get confused and think that gradient is just the reciprocal of resistance. It's not. It's just a way of quickly checking what the resistance is comparing two components. But you can't just say, oh, higher resistance, lower gradient, because you might have a non-ohmic component. Now, non-ohmic components, you're going to see curves. So if I pop this next to us like this, right in the middle, and let's say this is for a lamp. So for a, let's just rub out that part here, for a lamp, but not just any lamp, we're going to use a filament lamp. So this is a tungsten filament, a tungsten wire, pass a current through it, and the temperature of the wire increases. Well, remember what we said, with metals, higher temperatures, you actually have higher resistances. You can use the Drude model, D-R-U-D-E, if you want to understand why that is. But yes, higher resistances, higher at higher temperatures. That's the way metals work. And how do I get a higher temperature? Well, if we go back to here to power, we can see that if we have more current passing through our component, then more energy is being delivered per second for a given potential difference. And the potential difference is something that we are choosing. So for a given potential difference, if there's more current, there'll be more energy delivered per second. And what does that mean? Well, more energy delivered per second will increase the temperature of the filament, because that energy's got to go somewhere. It's going into the filament, it's going to go into the thermal energy store. So what you'll see is a graph that does something like that. It's not a great freehand one. Let's try it again, and let's go the other way. Curved up at the end. Not happy with that. That's even worse. Yeah, really try and get it as good as you can. Okay, that's about as good as I'm going to do, I think. So we have a region at this low current. If it's low current, it's going to end up with a low temperature filament. And so we have the resistance around here, which doesn't seem to depend very much on the current. But at higher currents, which happens at higher potential differences, the temperature of the filament increases, which then increases the resistance, decreasing the extra bit of current we get as we increase the potential difference further. So that is non-ohmic. Whereas this one is ohmic, because it's not a straight line. The last component that you'll need to know about is called the diode. And this is all stuff that's done at GCSE level, but you might have forgotten it. So let's do it again anyway. Let's pop that right over there on the right. Need to give myself a little bit more room there, don't I? Let's put that on the left a bit. What do you reckon there? Yeah, there. And I'll draw some delineating. I'll draw some lines like this, just so we can separate these different components. There we go. There we go. Okay, that's as good as we're going to do to try and get it all to... Oh, I could have just moved this to the left a bit. Okay, it doesn't matter. Shut up. I'm messing around. Let's rename this diode. And I can tell you now it's also non-ohmic for a diode. Now, diodes are very, very interesting components because in reverse bias, you get pretty much no current. It's teeny, tiny, tiny, tiny. We're talking microamperes, so it's pretty much no current. You can get a current passing through it in reverse bias with a high enough potential difference, but then it's not a diode anymore. You've broken it, sparked across it, and it's broken. So no current passing through it in reverse bias. And then there's almost no current in forward bias, actually. It doesn't just immediately start conducting. So you have no current, no current, no current, no current, no current, no current, and then there's a sudden change. And that happens at around 0.6 or 0.7 or 0.8 volts. Around about 0.7 volts, 0.6 volts. My textbook says 0.6. I've seen mark schemes that say 0.7. It's around about that. Should we compromise and say 0.65? Let's do that. It's a gradual change. It's a knee, but it doesn't happen straight away. That's very interesting. The reason why that happens I can go into detail with, but it's not required for your A-level, so I'm reluctant to do it now. But these are the characteristics you'll expect to see. So what does that mean? That means a diode will conduct. You get very, very, very low resistance when the potential difference is high enough, and very, very high resistance at much lower potential differences. So very low resistance, and here is very high resistance. Let's do that and just write it there. Very high resistance. We could say here resistance increases as temperature increases. Ooh, just made it fit. And here we can say that it's straight. There's no dependence. Okay. The last thing I'm going to talk about is this resistance and temperature thing. So diodes are interesting, and we'll have a look at diodes in more detail, a bit later on. Diodes are interesting and how they work, but we're going to leave that for now. And let's just talk about resistance and temperature. So, resistance and temperature. So with metals, it's absolutely true that at higher temperatures, the resistance is more. So if I were to plot a graph of, let's say, resistance versus temperature, in fact, I'm going to call it resistivity, not resistance. No, the title's resistance. I'll call it resistance. Resistance versus temperature. Could be resistivity, it would still be correct. What do we find? Well, we find we get a result like this, and we've already talked about that, and that is for a metal. And why is that? Well, because at higher temperatures, the ions are moving more quickly, which means there are more collisions per second with those electrons that are trying to flow, which means that the electrons transfer more energy per second to the wire, which increases resistance. So what about with non-ohmic conductors? What about with semiconductors? What about with thermistors? Well, thermistors will do something like, oh, not quite so dramatic, will do something like this. That is a thermistor. ER? No, OR. A thermistor. And why does that happen? Because at higher temperatures, more electrons are free to conduct. Should call them charge carriers. I said I wasn't going to talk about electrons conducting, but it's hard not to. Remember, we've got energy levels like this, and they get closer together, and we've got electrons sitting in these energy levels, and you give the electrons energy, they move up energy levels. When they fall down, energy is released, and all this sort of stuff we did ages ago now in the course. Well, it turns out that with certain substances, particularly things around group 3, 4, and 5, you've got your energy levels like this, but then you've got a band of energy levels and a band of energy levels, and there's a band gap. And if you can get electrons to jump up over that band gap, then they're in a band which we call the conduction band. And in the conduction band, those electrons can move to the neighboring atom because there's no electron in it, and atom next to that, and so on and so on and so on, and drift through the crystal lattice of this semiconductor with very, very little impedance. If electrons, however, don't have enough energy to be in that conduction band, then they stay in what's called the valence band, and that's those electrons are shared between the neighboring atoms in the covalent bonds. So with thermistors, you increase the temperature, more of those electrons, because of collisions between neighboring ions, more of those electrons get enough energy to move into the conduction band, and so we have current that increases because there are more charge carriers, meaning a reduction in resistance. Whereas with LDRs, light dependent resistors, it's the same basic principle, but we have chosen that band gap. We've modified the metallurgy, we've modified the materials so that the band gap is related to visible light photons. They carry enough energy to promote electrons into that conduction band. And we can even combine these semiconductors in interesting ways, extrinsically doped semiconductors, to produce things like diodes and transistors. But that all lies beyond this this A-level course. Oh, I do have to talk about negative temperature coefficient, of course. So we say a metal has a positive temperature coefficient because the relationship between resistance and temperature is a positive one. So we say this has a positive temperature coefficient, and thermistors have a negative temperature coefficient. So this is a PTC, this is an NTC. And I'll just double check that I have write it properly. I'll just double check that I've covered everything that needs to be covered. I think so. You can see clearly that the metals are almost linear. They're not quite, but thermistors are non-linear, definitely non-linear. Yeah, I think we're happy with that. We've covered quite a lot this lesson, but that is the end of the section, the first section of electricity, electric current. We'll be moving next lesson on to a new section, direct current circuits. This is where things start getting a little bit trickier. So I hope you'll join me then. Bye-bye.